Okay, let's dive into this explainer. Today, we're running an extreme science thought experiment. We hear about killer rocks from space all the time, right? But the focus is almost always on them hitting land. But hey, our planet is actually 71% water. So, what if a mountain sized asteroid drops straight down right into the deep ocean? We're going to explore the terrifying, awe inspiring physics of this exact scenario. We want to figure out exactly what happens when the unstoppable force of the cosmos meets the immovable depths of the sea. Imagine it, a rock larger than a skyscraper, maybe the size of Mount Everest or the entire footprint of Lower Manhattan, falling from space and crashing directly into the middle of the deep ocean. Just picture that exact cinematic moment. The sky suddenly, violently lights up with a blinding flash that would completely outshine the sun. This massive rock hits the water at unbelievable speed, and instantly a gigantic explosion of steam and dark seawater shoots miles up into the stratosphere. The sound alone, it would literally shatter windows thousands of miles away. So, could one asteroid crash change the entire planet? That's the massive, high-stakes question we're posing today. We aren't going to give away the answer just yet, but think about it. When a pebble hits a pond, you get tiny ripples. But when a mountain-sized rock hits the ocean, what actually happens? Does the vast ocean act like a giant planetary airbag, magically absorbing the blow to keep us all safe? Or does it trigger a catastrophic chain reaction? Let's build this scenario step by step to find out. Section 1. The cosmic bullet. Before the moment of impact, we really need to understand the physical properties of this asteroid. Our asteroid is extremely large and it's moving incredibly fast as it approaches Earth. Let's say it's traveling at 45,000 miles per hour, which is vastly faster than a speeding bullet. As you look up from the ground, the object just gets brighter and brighter. The atmosphere begins heating around it, glowing with intense friction. But down below, the ocean remains completely calm. The water has absolutely no idea what's coming for it. So the crucial point is this. Both the massive size and that extreme speed give this asteroid an enormous amount of kinetic energy. And kinetic energy is simply the energy an object has just because it's moving. A baseball thrown by a kid has a little kinetic energy. A mountain-sized rock traveling at tens of thousands of miles per hour, that holds an almost unimaginable amount of energy, equivalent to millions of megatons of TNT. And the laws of physics dictate that all of that energy has to go somewhere the exact second it hits. Section 2. The ocean impact. Let's transition to those exact final seconds of the calm ocean just before the dramatic strike. The immediate aftermath is absolutely devastating. When it hits the water, the asteroid transfers all that kinetic energy instantly. First, a massive shockwave blasts outward, traveling faster than the speed of sound. Next, the water directly beneath the asteroid is superheated in a fraction of a second, creating huge amounts of steam and violently throwing millions of tons of water into the air. Finally, it literally punches a temporary hole in the ocean, a rapidly expanding crater miles deep. And exactly how this result plays out depends heavily on the asteroid's size, its speed, the angle, and the location. Let's move to and see how this builds, because not every single wave is a tsunami. It all starts with massive water displacement, the asteroid physically shoving the ocean out of its way. Then, as that immense energy travels, it interacts with the seafloor. The depth and shape of the ocean floor actually act like a giant lens, focusing and steering the energy, which ultimately dictates the coastline impact. True danger really depends on that water displacement and the seafloor shape. If it's deep enough, this chain reaction creates a wall of water moving at jet plane speeds right toward land. Section 3. Beneath the surface. Let's plunge beneath the water to see what happens to the environment right after the shockwave travels through the ocean. The immediate devastation to marine ecosystems near the impact zone is absolute. The sheer force of that shockwave would instantly destroy life across a massive underwater area. We're talking about completely wiping out local fish populations and shattering coral reefs. But incredibly terrifying is the effect on plankton. This impact literally incinerates the foundation of the marine food web, ensuring nothing can survive there for years. The seafloor itself is left completely scarred. Section 4. The sky turns dark. So, what happens next as we move our focus from the ocean depths up into the Earth's atmosphere? And this brilliantly illustrates the sheer scale of the event. We are contrasting the underwater devastation with the vapor and dust thrown high into the sky. An enormous impact throws unfathomable amounts of water vapor, pulverized rock, and vaporized salt into the atmosphere. All those particles basically create a planetary shield that can block sunlight. And if sunlight is blocked, global temperatures drop. Now, not every ocean impact causes a sudden global winter, but the atmospheric changes affecting sunlight and temperature could be severe and widespread. Section 5. The human cost. Now we shift our focus to human civilization and answer the question, could this impact send huge waves around the entire planet? Yes, waves can travel enormous distances through the open ocean, and the secondary effects on humanity would be staggering. Depending on the asteroid's size, how the continents are shaped, and ocean depths, coastal cities could face catastrophic flooding. Coastal infrastructure, ports, and massive cargo ships would be ruined. Fishing and global food supplies, disrupted overnight. Even the underwater fiber optic cables that power our communication could be severed, and global transportation and trade would grind to a sudden halt. Let's break down the timeline of the world after the impact. In the immediate days and weeks later, we'd see physically altered coastlines and wildly disrupted local weather from all that atmospheric vapor. But looking months and years later, we begin to see the true dread. Those short-term disrupted weather patterns cascade into devastating global climate shifts and severe ecological consequences that could suffocate agriculture and alter human survival for generations. Section 6. Land versus ocean. This introduces the biggest twist and question of our thought experiment. Is it actually safer if an asteroid hits the water instead of the land? Now, what's really interesting about this slide is that the answer isn't a simple yes or no. Weighing the outcomes reveals that an ocean impact triggers extremely complex and devastating global effects. Sure, the ocean might spare us the direct destruction of dropping a space rock right onto a populated city. But enormous water displacement creates unpredictable, world-traveling waves. The marine destruction is immense, and the atmospheric effects from injecting billions of tons of water vapor and salt into the sky can alter the climate just as dangerously as a land impact. Now, obviously, we cannot realistically drop an asteroid into the ocean as an experiment. Scientists study these fictional thought experiments to understand the physics and better prepare for real threats. Understanding the mechanics of kinetic energy, water displacement, and atmospheric changes really helps humanity plan our planetary defense. It helps us develop massive deflection strategies and precise trajectory mapping to protect ourselves against real objects that might one day approach Earth. Which leaves us with one memorable final question. If you could choose where a giant asteroid would hit Earth, would you choose the ocean, hoping the water magically absorbs the blow, or would you never take the risk? We study these scenarios now theoretically because sometimes the most dangerous experiment is the one you only get to try once. Thanks for joining me on this explainer. Keep wondering what happens next.